Hello, welcome back. Similar to the last part, this video for the second part of Chapter 2, Section 4 has a lot of notation and formulas. Make sure you're keeping those straight in your notes, not just in the lecture notes. Those lecture notes are meant to help you, but come test time, it'll help to have some notes that have just notation and formulas and what they're for on them. Okay, let's dive in. Welcome back for Part 2 of Chapter 2, Section 4. If you recall from the last video, we made a lot of connections between a dataset's center and its variation. In particular, we discussed the importance of center and of standard deviation. The center anchors the number line, and the standard deviation gives us an idea of spread, i.e., how far away a typical data entry could be located from the center. Now that we've made these connections between center and spread, what we want to do in this video is make some connections between standard deviation and the shape of a distribution. The first connection we'll make is perhaps the most used rule in statistics. It's called the empirical rule, or the 68-95-99.7 rule. This rule is strictly reserved for data with a symmetric bell-shaped distribution like this. The empirical rule allows us to interpret proportions of a symmetric data set using its standard deviation as a partitioning tool. Before we get to the rule, let's talk about notation. If you notice at the bottom of the graph, there are actually two lines of labels. This is not the way a graph like this would normally look. Which of these rows of notation you use depends on whether you're working with population data or sample data. If you look at the key in the rectangle towards the top, you see an explanation of the different notation we've been using. X bar is the sample mean, S is the sample standard deviation. Mu is the population mean, and sigma is the population standard deviation. If you'll notice, one row has the notation for working with sample data, the top one with X bar and S, and the bottom row has the notation for working with population data. I just wanted you to see what the different types of notation might look like for this type of graph. Just remember that you need to pay attention to which data set you're using so you'll use the correct notation, as you will only use one of these rows to label your distribution. So if you look at the bottom center of the graph, you'll notice the two notations for the mean, X bar for the sample mean and mu for the population mean. As you move out a unit, you are actually moving one standard deviation away from the mean. That's why it says X bar plus S. The sample mean plus the sample standard deviation. If you move out one more, you are at the point 2 standard deviations above the mean. So it says X bar plus 2S, or 2 standard deviations, and so on. This also works the same way on the other side of mean, except we are subtracting standard deviations from the mean. The second one is subtracting 2 standard deviations, and the third is 3 standard deviations away from the mean. Okay, now we have the layout. Let's see what the rule says. For data with a symmetric bell-shaped distribution, the standard deviation has the following characteristics. About 68% of the data points lie within one standard deviation of the mean. Since the graph is symmetric, this means we also know that half of that 68%, or 34%, will lie to the left of the mean, or center, and 34% will lie to the right. Notice where this hits our labels at the bottom. One standard deviation greater than the mean and one less than the mean. 68% of all the data in a symmetric data set lies within one standard deviation. Next, the rule says that 95% of the data in this type of data set lies within 2 standard deviations of the mean. See how the spot 2 standard deviations away from the mean on either side has been circled? The rule says that 95% of our data in a symmetric data set lies within 2 standard deviations of the mean. Lastly, the rule says that about 99.7% of the data lie within 3 standard deviations of the mean. The graph has the last percentages around that section marked as well, so you can see how much of the data is outside of that 99.7%. It makes sense that when you subtract that from 100, you get 0.3% or 0.15% on each side. That is the part of the data that lies outside of 3 standard deviations of the mean. If you look at the percentages, you can see that we could figure out what percentages of data lie above or below a certain data point, given its relationship in standard deviations from the mean. We'll talk more about that later. Here's a summary of the rule again. 68% within 1 standard deviation, 95% within 2 standard deviations, and 99.7% within 3 standard deviations of the mean. Something else to take away from this is that the data points beyond 2 standard deviations are very rare, and the data points beyond 3 standard deviations are even more rare. So when they occur, they have more of an effect on the mean than the data points lying closer to the mean. Let's work through an example using the rule. In a survey conducted by the National Center for Health Statistics, the sample mean height of women in the United States ages 20 to 29 was 64.1 inches, with a sample standard deviation of 2.6 inches. Estimate the percent of the women whose heights are between 58.9 inches and 64.1 inches. First, we need to note the important information in the problem. They gave us the sample mean height of 64.1 inches. They also gave us the sample deviation of 2.6. So now let's use proper notation for these pieces of information. This means that x bar equals 64.1 inches and lowercase s equals 2.6 inches. From that information, we're able to graph the distribution of women's heights as shown here. The sample mean anchors the graph at 64.1. Then we simply add 2.6 to it to find our first marker above the mean. Then subtract from it to find our first marker below the mean. Then add it again to get the next marker above, and so on. Because the distribution is bell-shaped, we can use the empirical rule to find the percentages between the heights. The mean height is 64.1 inches, and the height in question is 58.9 inches. We need to find out where the height in question lies in relation to the mean, so we subtract it from the mean. 64.1 minus 58.9 equals 5.2. Now, how does that number relate to the sample standard deviation? We find this by dividing 5.2 by the sample standard deviation 2.6. Our result is 2. This means 58.9 is 2 standard deviations away from the mean. Because our numbers line up nicely with the standard deviation markers, we can use the percentages from the empirical rule, which say that 34% of the data lies between the mean and the first standard deviation below the mean, and 13.5% of the data lies between the mean and the second standard deviation below the mean. We can now add those and get 47.5%. This means that 47.5% of women have heights between 58.9 and 64.1 inches. The empirical rule helps us quite a bit. Just knowing the shape and a few statistics gives us a lot of information about the distribution as a whole. But the empirical rule does have limitations. As we've said, it can only be used if the distribution is bell-shaped and symmetric. What if our distribution is not bell-shaped or we don't know what it looks like? That's when Chebyshev's theorem comes in. Chebyshev's theorem states that the portion of any dataset lying within k standard deviations, as long as k is greater than 1 of the mean, is at least 1 minus 1 over k squared. Now, in order for this approximation to make sense, the value of k has to be strictly greater than 1 because we're interpreting k as the number of standard deviations. So, for instance, when k is 2, at least 75% of the data lie within 2 standard deviations of the mean because 1 minus 1 over 2 squared equals 3/4, or 75% of the data. If k equals 3, at least 1 minus 1 over 3 squared equals 8/9, or about 88.9% of the data lie within 3 standard deviations of the mean. Let's do an example using this theorem. The age distributions for Georgia and Iowa are shown in the histograms. Apply Chebyshev's theorem to the data for Georgia using k equal 2. What can you conclude? Is the age of 87 unusual for a Georgia resident? What about for an Iowa resident? Pause the video and see what you can reason out for yourself. First of all, notice the shape of these distributions. Neither of them is bell-shaped or symmetric, so we can't use the empirical rule to decipher anything about proportions about either data set. Let's look at Georgia first. K being 2 means that we are examining 2 standard deviations above and 2 standard deviations below the mean. The graph gives us the mean of 38.2 and the standard deviation of 22.6 years. 2 standard deviations below the mean would give us negative 7.0 because 38.2 minus 2 times 22.6 equals negative 7. Now, how do we interpret this in the context of the problem? Well, age can't be negative, so our lower bound is down to 0 or birth. Now, 2 standard deviations above the mean, or 38.2 plus 2 times 22.6, which equals 83.4, is our answer for 2 standard deviations above. So you could say that at least 75% of Georgia's residents are between the ages of 0 and 83.4. So an age of 87 would be outside 2 standard deviations away from the mean, which makes it unusual. So an age of 87 in Georgia is unusual. Okay, let's see about Iowa. Again, we're curious about the age range that is 2 standard deviations above and below the mean. Using the mean and standard deviation provided with the graph, we use the Kate's value of 2. We are able to determine that 2 standard deviations below the mean of 39.8 is negative 7.6, or as we did for Georgia, 0 or birth. And 2 standard deviations above is 39.8 plus 2 times 23.7, the standard deviation, which gives us 87.2. So this tells us that at least 75% of the population lies within the range of 0 to 87.2 years old. Now the age in question, 87 years old, is within the range of 0 to 87.2, so it would not be unusual for someone to be 87 years old in Iowa. Now let's think about a situation where the only information we have is a frequency table. How do we go about finding a standard deviation? Remember, in a frequency table, we don't have access to the raw data values. We just have a tally for the number of data points that fall into each class. Do you recall what we did to find the mean of a frequency distribution? We used the frequencies and the midpoints. Well, we can use that same estimation logic to approximate the standard deviation for group data as well. And lucky for us, the formula is not that different from the regular standard deviation formula. We take the square root of the sum of the products of the squared deviations times the frequencies for each class, divided by n minus 1. The value of x in this formula is assumed to be the midpoint of each class. Let's do an example. The figure shows the price ranges in thousands of dollars and corresponding number of homes recently listed for sale in a mid-sized U.S. city. Make a frequency distribution for the data. Remember, that means a table for the data. Use the table to estimate the sample mean and the sample standard deviation for the set. First, we need to construct a frequency distribution. Because the highest class of 500,000 or more is open-ended, we must choose a value to represent the midpoint, such as 599.5 thousand. As the table here shows, we create the frequency distribution by finding the midpoints of the classes, which are represented by x in the table, then the frequencies of each of the classes. Then we find the product of each of the classes and their frequency. Once we sum each of those, we divide the sum of the products by the sum of the frequencies to get our mean of the frequency distribution. In this case, we have 60,255 divided by 390, which is about 154.5. What does this mean? We can translate this as the mean price of houses in this mid-sized U.S. city is about $154,500, which is the sample mean. Next, we want to find the standard deviation. So we need to find the individual deviations or differences from the mean, as shown in the first column. After that, we square each of the deviations, then multiply them by the frequencies. This gives us a sum to work with for the numerator for our formula. We then divide that by the number of data values in our set, minus 1, or 389, and take the square root of that number. Our result is 139.4, which is our sample standard deviation. An appropriate estimate for the sample mean is $154,500, and an estimate for the sample standard deviation is $139,400. Let's see how this would work on the calculator. You want to enter all the midpoints into the L1 list and the frequencies into L2. As a reminder, you get to those lists by pressing Stat, then making sure Edit is selected and click Enter. Then press Enter between the entries as you put them into your calculator. You'll need to arrow over to L2 once you've finished entering L1. Then, to get to the one variable statistics menu, you press Stat, arrow over to Calc, then press Enter. At this point, your calculator could give you a number of options depending on how old your calculator is. You may have to type L1, L2. Some will have the data lists available to choose from. Others will have the list : and have L1 as the default, but not have anything next to frequency, in which case you need to press the second button and then the number 2. Whichever of these options you need to do for your calculator, what you want to end up with is that the data is coming from list 1 or L1 and the frequencies are coming from L2. Then you will need to press Enter and Enter again for it to process. Your results should be the same. It should be drawing data from L1 and frequency information from L2. Then you press Enter again. How much simpler was that, besides the entering the L1 and L2 part, which you'll get the hang of. Once you understand your calculator, it will go much more smoothly. Now you know the hard way, and fortunately for you, the easy way, now available to you by using the calculator. Remember these steps or write them down for later use so you won't forget how to do this in the future. Now we're going to cover one more point in this video, and it's what you do when you can't use standard deviation to compare data, either because they have different units or different means. We use something called coefficient of variation. The coefficient of variation, or CV, describes the standard deviation of a data set as a percent of the mean. It is literally a ratio. You find the CV for a population data set by dividing the population standard deviation of a data set by the population mean and multiplying by 100% to get a percentage. For a sample data set, the coefficient of variation is found by dividing the sample standard deviation S by the sample mean, or X bar, and multiplying it by 100% to get a percentage. We have two formulas here simply to reflect the difference in notation, which again depends on the type of data set we're working with, population or sample. The table shows the population heights in inches and weights in pounds of the members of a basketball team. Find the coefficient of variation for the heights and weights, then compare the results. The formula for CV requires the population standard deviation and mean for these data sets. So let the calculator do the work for you. Type your heights into L1 and the weights into L2. Press the Stat button, make sure Edit is selected, then Enter and enter your data. After you've done that, press the Stat button, arrow over to Calc, choose one variable Stats, and specify L1 and hit Enter. You may have to press Enter more than once depending on your calculator. Note the information you need for the problem, namely the mean height and the population standard deviation. You'll need to do this for L2 for the weights also. The mean for heights is 72.8 inches with a standard deviation of 3.3 inches. We can now find the coefficient of variation by dividing 3.3 by 72.8 and multiplying by 100%. This gives us 4.5%. The CV for heights is 4.5%. Now we can do the same for weights. The mean for the weights is 187.8 pounds with a standard deviation of 17.7 pounds. We divide 17.7 by 187.8 and multiply by 100% and get 9.4%. When we compare the two CVs, we see that the weights with a CV of 9.4 are more variable than the heights with a CV of 4.5%. That's what we're measuring here, the variability. This concludes Chapter 2, Section 4. I know this was a long one, but you got through it. I will see you in the next video.